All right, so here we are again, a new semester. It finally started. It's snowing today. It's February 1st. It seems late for us to be starting, but of course, these are not normal times, are they? So everyone received, I see the invitation that I sent you. That's good. That's how we're going to work it throughout the rest of the course. I'll be sending you an invitation. Even though I've set this meeting up to repeat every Monday at this time, and Thursday, I think you still need a new link every time we start. So I will send you one every time just before we start, usually the day before. Hopefully, very occasionally I do forget about it and I don't send it to you until just a few minutes before the class starts. But even then, you'll have it in your inbox before we start. So all you have to do is click it on, and I see that it didn't cause any problems for anyone since you're all here, just about. So anyway, so now, of course, this week also people may still be joining the class, and so we'll try to get everything straightened out. So, all right, why don't we wait a minute until everybody's arrived, and then we can get started. And so everything we're doing here is being recorded. So when we're done, if you missed something or if you just want to watch it again, you can watch it whenever you want to. Now, it turns out that Zoom is not really set up well for storing recordings. If you look at Moodle, or actually not Zoom, Moodle, sorry. Let's go to Moodle for a second and take a look at where we're going this semester. Let's see, let me go find it. Here we go. Okay, so here's our Moodle page. And you'll see that so far I've posted the syllabus, which we'll be looking at in a minute, and the first 3 parts of chapter 5. They're broken up into pieces because they're all fairly large documents. These are all PowerPoint slides. And I don't know, sometimes when they get too large, it can cause problems. So it's broken up into 3 pieces. Now, if we had the capacity for it, I would put the videos right in here, but it doesn't apparently work very well. So what we're doing as a compromise is we're putting them in YouTube, as a matter of fact. So if you go to YouTube, which you're all, I'm sure, very familiar with, you'll find that maybe you have your own page, maybe you don't. I have my own, which I've set up just for this purpose. And you go to my channel. And now what happens is when you get here, I think as far as I can tell, you can find me just by typing in that name. I don't think you need any other information. And then what you should do is look under playlists, because I have a lot of classes this semester. And so in order to avoid having them all the videos jumbled together, I've created a series of playlists. And so what you should do is look in yours. Oops, no, not that one. Right now, I guess you won't see anything because there are no videos in them at the moment. But what'll happen is once we start posting videos, there'll be a separate playlist for the 8:30 session of this class, and all of the videos will be there, and you can watch them or not watch them. It's up to you. But of course, the advantage again is that if you missed the class, you can catch up, or if you didn't quite get everything we did, you can watch it again. And so far, I've found this system is working fairly well, except for the fact that we can't put them on Moodle, and we have to come over here to YouTube, but that doesn't seem to be a problem. The only thing is about watching on YouTube, I don't know if they have a way of sneaking in commercials on them or not. I hope not. That wouldn't be right. But basically, this is where you can find the videos as soon as we're done at the end of the day. All right. So why don't we do this? Now, we'll go back to Moodle. And well, again, just to remind you, what I have here is the syllabus plus the first chapter is broken up into 3 parts. This is going to take us a while to get through. This is a fairly long chapter, which is essentially a review of many important concepts that you probably run into before, but maybe it's been a while. In fact, it could have been a couple of years since you had your last math class. Now, that reminds me too, I have this tool that I can use here, which is kind of fun. I can actually create polls here. And so I think what I'd like to do is just to get some practice with this, I'm going to create a question right now. And again, this is just for the fun of it. Here's the question. How long has it been since your last math class? So what they let us do is have a multiple choice. The first one will be less than a year, 1 to 2 years, and then more than 2 years, let's say. That should do it. I would normally ask the class this question in person anyway, if we were actually in the classroom, but I think it's more fun this way anyway. So, oh God, what happened? See, I'm still learning how to use this stuff. And I think I may have accidentally lost my work. Oh boy. Okay, I think I blew it there. All right, let's do that again. Let's try that one more time. When I'm finally done with it, you'll see it pop up on your screen, and you'll have the ability to vote. Okay, here we go. I'm going to try it again. It's not exactly user-friendly, this thing, so bear with me. That should do it. I have no idea what happened, why it didn't work. See, what's not here is the word save, and that's what's really annoying about this thing. Click save.
Save is on the bottom. Save is all the way at the bottom.
Do you see a save button there? I don't.
It's right next
to
it. Your mouse is right above it.
Okay, no wonder I couldn't find it. Well, that explains that. All right. All right, so now I have to go back here. Here it is. Now, when I hit this button, it should pop up on your screen, and then you can vote. Oh, wow, it's a mixed bag. Okay, we do have some people more than 2 years. Wow. And then 1 to 2, I figure it would be about that. All right, well, that's a pretty normal set of responses, I would say. That's pretty much what I usually get. All right, well, since that worked pretty well, let's do this. I'm going to create a new one. Okay, how do I do that? All right, here we go. Okay, here we go. Whoops, no, that's not what I wanted. Let's get that going back here again. Oh boy. You do see what I mean about, this is really a very awkward, in my opinion, extremely awkward setup, but I'm going to try it again. This should be fun. All right, let's try that again. Love it. I'm okay with it. Don't ask. Okay. All right, let's try that one. Okay, now let's see. God, this is so annoying. I would like to know how to run that one I just created. It doesn't seem to have that capability. Oh, here we go. All right, here we go. Let's try this one. This is an interesting one. I always ask this one too, usually at the start of every semester, and it's interesting to see the range of responses. When you're in person, you get a little bit more emphasis. The people who really don't like it, they really don't like it. You don't get a lot of people who are willing to admit that they love math, but there are a few of us, and a lot of people are just, it's okay. And then there's others who think, well, maybe my life would be better off without it. But so that's okay though, because I think you'll find that what we're doing in this class is pretty down to earth. It's not very theoretical at all. You may have run into that in your high school math classes. And to the extent that's possible, we'll try to introduce applications for the content when we see it. I usually have lined up a series of videos, which we will watch during the course, that help us get some more background about what this is all about, and hopefully give you some insights into what math can be used for. Because if you can see the big picture, like what are we supposed to do with this stuff, that might help make it less or more, let's say, more interesting to you. And but let's face it, if you don't like it, you don't like it. But I mean, it's also going to be helpful, I think, if you at least have some sense of what it's meant to be used for. And so we'll do that. We'll mix those in throughout the course as we go along. There's quite a few that I have that are actually quite interesting. I mean, when you go to YouTube, there's a lot of crap on YouTube, but there's also a lot of really good stuff as well if you know where to look for it. So we'll go through that as well. Anyway, so why don't we start? I think everybody should be here by now. I've forgotten exactly how many people are in the class, but this looks like the right number. So what we're going to do now is go back and revisit. Let's see. Some Moodle is now. Here's the problem. I've got so much crap open up here. I have to go. Here it is. Why don't we open up the syllabus? And by the way, if you have any issues getting into Moodle, or anything really for that matter, you can just let me know right away. My email address should be, there it is. It's on here. You can get in touch with me. Now, if you may have noticed, when I sent the invitations out, they actually did not come from this email address. They came from another address. And the reason for that is because your roster is in an Excel spreadsheet, which I created myself. And in order to send out a list, for whatever reason, the purchase email doesn't accept lists like that. So in order for me to send you an email with an invitation, I would either have to type your names individually on the purchase email system, or else use my own Gmail account where it will directly accept those Excel lists. So that's why you might have noticed that when you got your invitation, you're like, well, who is this person? I sent it out from this account. It's Dr. AA. Let me send you anyway, there it is, sent. There, no, there's a lot of them. You got one of these is yours. But anyway, so the account that I use here is, let me just write this down somewhere in case you need it. If you do need to get in touch with me, there's a lot of ways you can do that. Let me make it bigger in a second. But this is the one, I use this account all the time. So I'm going to see this one pretty quickly. If you send me an email, say, oh my God, I can't make it to class tomorrow or something like that, you can use my purchase account or you can use this one. It doesn't really matter, but I'm going to send out the invitations from this account just because it's easier. And it's okay with me if you know my email address. I figure you're not going to send me anything that isn't school related anyway, so that's okay. That this is not a problem. So it's draa2012@gmail.com. I used to put it on the syllabus. I guess maybe I should go back to doing that. But this one is my purchase account. Now, when we do start having assignments, though, which we will eventually, then you can email them to the purchase account because it's easier for me to keep them all together in one place. But we'll talk about that later. All right. Now, in the meantime, this is your typical syllabus that you'll get at SUNY Purchase. You got my name. Now this is the part that's unusual. Normally there'd be an actual name of a room here. We might be in the Natural Sciences building or the Social Sciences building. Not now. We're all going to be online. Now, having said that, some of your classes may actually be held in person. Oh, I know. What a great idea for a poll. Let me see if I can get this together really fast without messing it up. Classrooms. Do you have any in-person classes this semester? Now, this is just obviously yes or no. All right. Now, there we go. Let's try that one. This is the kind of question I don't normally have to ask, but this semester, yeah. Okay, well, it's actually larger than I expected. Because last fall they pretty much closed the school to everybody except performing arts students who had to be there. I don't know. They claim that they were going to start changing that slowly this spring. Does anyone have a class in person which is not related to performing arts? Okay, that one I'm verbally asking you, so you actually have the ability yeah, there we go. Extended media. Oh, okay, that's cool. Do you have to wear masks in the classroom?
Yeah, we have to wear masks.
Do you have to like not sit next to each other?
Yeah, like my last in-person class in the fall was 3D processes, and we had to have like really far away desks in order to do any of our work. And we also have to wash our hands constantly when using metal shop. So like for the few art classes that were in person, we had to take a lot of precautions in order to do what we needed to do. So yeah.
Yeah, okay. But I can see why, because a class like that, you can't really do it online, can you?
Nope.
No, it doesn't really make a lot of sense. Or like dancing or piano or art, come on. It doesn't work online. But a class like this, you can do online. It's not the same, but it's not a terrible substitute for it either. So, and plus, let's face it, when the class this early in the morning, by having it online, you don't have to get up quite so early, do you? Because nobody can see you if you don't want them to. You could have just rolled out of bed 2 seconds ago and nobody would know the difference. So, all right. I was just wondering, but I think, well, I don't know. Nobody knows. But I think my opinion is that by the time September rolls around, we might be more or less back to normal, but who knows? There's no way of knowing. But anyway, in the meantime, here we are. So let's get back to these syllabus. Where is it? There we go. Okay, so what do you actually need to know for today? All right, so there's a book. If you're in the bookstore, if you're actually on the campus, they're very, very rigid about who can come onto the campus. Like if I wanted to go to my office, I think I'd have to call them up and let them know in advance that I'm coming. It's really not like you can just go back to the campus any longer. It's pretty well restricted. But if you do have the ability to go to the bookstore, you'll see that this book is in a big pile somewhere because all the Math for Contemporary Life books courses use it. And it's got a big pizza on the cover, so you can't miss it. Now, having said that, you are not required to own this book. The notes are all in PowerPoint slides anyway, but it's a nice book. If you like to have textbooks, if you want to read more about this content, that's the book that you should get, but it's not required. I don't know if they've ever, it's a pretty old book. I do not know if there is an electronic version of it available. I haven't actually checked that out. I do know that I haven't bought a real book in years because everything now is in my Kindle app because it's just so convenient. I just couldn't be bothered anymore with physical books because I don't want to carry them around. I don't want to lose them, et cetera, et cetera. Now, the calculator. This is an interesting question. This is also poll worthy. I'm going to ask you, because this is not necessary, do you have a physical calculator? Now, whether you say yes or no, nobody's in trouble or anything. I'm just curious about this. All right, no. Ooh. All right, let's check this out. Man, that's a pretty high percentage. Okay, well, that's good to know. Now, I'll tell you why I'm asking this question, because you don't have to have a physical calculator for this class. If you do not have a physical calculator, you may or may not be aware of it, but your iPhone has a calculator app built into it, and it's a really nice one. But there's a secret that you have to know to use it. Okay, so what would be that secret? Let me see if I can show you this this camera. Hold on a second. So you go to your phone, look at all the apps, all those pretty little apps. The calculator comes with it automatically. Now, here it is. The thing is, that is your standard basic calculator. It can hardly do anything except the very basic functions. So what you want to do is turn it sideways. And what happens is it turns into this amazing scientific calculator. If you didn't know that, you wouldn't ever find it. So once again, it's in this big pile of, oh God, I don't think you can see that. There it is. All right, it comes with a phone. I don't think you can even delete it. It's right there when you buy the thing. Even if you only have one app in the phone, this is the one, okay? So once you grab that, remember, turn it sideways into what they call landscape mode, and it suddenly turns into a full-blown scientific calculator, which is perfectly adequate for this class. So what I'm going to do is, as we go throughout the class, we're going to use the calculators fairly regularly, and we're going to learn how to use this thing, because there's, every calculator is a little bit different. They all have their own quirks, and you have to learn how to use yours. You want to get good at one calculator, and this can be the one. So if you have a different one that you're good with, go right ahead, keep using it. Whatever you're comfortable with is what you should use. But if you don't actually own a calculator, you can use this one. It's a very good calculator, actually. But you do have to learn how to use it properly. That's good. All right, so that takes care of that. Oh, I didn't realize that. Oh, okay. Anyway, now if you happen to have one of the really high-end ones, like the Texas Instruments 84, let's say, that's good. That's going to help save you a lot of grief, but then it's understood that you have to, you have to, it's a little bit harder to learn how to use it. That's the trade-off with the more sophisticated calculators. It's great, it's very powerful, but you have to learn. So maybe later on we'll do a survey about who's got what calculator, but at the very least, we'll definitely go over the keystrokes that you need for using the iPhone. And of course, the good thing about the iPhone is that you never leave the house without it, do you? No, you might forget your calculator, but you're not going to forget your phone. So no matter where you are, you'll always have this phone with you. All right, now, what else do we need to know? Well, this is a math class, of course, so we're going to have tests. There's going to be 3 of them. These are the topics that we'll be covering, and what I'll be doing is, as you saw here already, chapter 5 is posted. It's broken up into 3 parts. We'll go through it, and as we go along, I'll keep posting more and more. And then also, we're also going to do a lot of problem sets, because this is the kind of material that lends itself very well to practicing. In other words, learning this material is not unlike learning the piano, because it's just a question of practicing. Of course, you have to have some skill, but I mean, you have to practice to get good at this stuff. And so we're going to do a lot of problem sets throughout the course just for the practice. Okay, the actual scoring, your actual final grade will come down to these 3 exams, which we'll discuss as we go along. And wow, other than that, now there's a lot of also this other discussion here. There's a discussion here about disability, the Office of Disability. If anyone has an issue, you can discuss it with them. You can often get, it doesn't make as much sense online, but when we had physical classrooms, some people were allowed to take more time, or some people, there were other extenuating circumstances. This all comes to the Office of Disability. If you need them, this is how you get in touch with them. Other than that, I think we're good. There's not much else we can say here. So I think what we want to do today, now I know it's the first day and I know it's early in the morning, and math maybe isn't the best subject to be doing first thing in the morning, but what I'd like to do is at least get the ball rolling here and get started. And you'll see as we go along that while you might recognize a lot of this content, at least in the first chapter, it might be the case that you're starting to get a little rusty, and that this will help bring it all back into your memory. And also, if you just think about math on a regular basis, a lot of the knowledge that you've accumulated over the years will start to show up again, and it's suddenly there and available when you need it. It's kind of like going out jogging again after a long layoff. Let's say that it's been a long winter and you haven't been able to get outside and run. Now you're starting to run again, and it's going to hurt for a while, but then you'll get used to it and you'll actually get better at it. Okay. So, all right. So this is chapter 5. Let's get it open. And you can see it's on PowerPoint slides. And all right, so we got 28 people. Okay, that's good. And I think we'll start here. So, all right, so we're going to start by looking at the so-called real number system. Now, you might remember from your travels that there are really two basic kinds of numbers that you can encounter. In fact, let me just briefly remind you that all numbers are either real, or what, does anyone remember what the other type of numbers are called? I'll give you a hint. It starts with an I. Oh no, we got it. Okay. No, imaginary. That's it. Yes, yes, it's coming back. Imaginary. Okay, now, what exactly is an imaginary number? Now, you might say to yourself, is this for real? An imaginary number, how can a number be imaginary? Okay, well, what happens here is you probably remember that you cannot take the square root of a negative number. Or can you? Okay, so let's, by the way, I have this wonderful math editor that I use in this class. Okay, let's try this. Okay. So what you're seeing here I wonder how to make this bigger. Oh, there we go. Okay. You notice, you might recall this from wherever you've had a math class before, that little I represents the square root of -1, which is defined as an imaginary number. Okay, so we disallow for that in the real number system. Now, in this class, we're only going to be focusing our attention on real numbers. Okay, so it's good that you know that imaginary numbers exist, but we're not going to use them in this class. This is meant for a much more advanced situation. Okay, so it's good to know that these exist, but in this class, we're only going to focus on real numbers. Now, you might also recall that the real numbers can be illustrated with a graph that looks something like this. Hold on a second. It's basically just a line. And it has numbers like 0 and 1 and -1 and 2. And it goes out all the way to positive infinity on the right-hand side and all the way down to negative infinity on the left-hand side. And in between, we have all the other numbers, the fractional numbers like 0.402 and 1.171, -1.3456, let's say. So all the real numbers are incorporated onto this line, and there are an infinite number of real numbers. Although now that I think about it, if you want to be crazy technical about it, this should say is, because is refers to infinite. There's an infinite number, or the number, sorry, there is an infinite number of real numbers on this line. And so what we're going to start doing here is classifying them into different categories and starting to understand their properties. Okay, so all the numbers you might encounter in the real world are actually we call real numbers, but we can break them up into several very interesting categories, which may or may not sound familiar to you. All right, so we'll start with the so-called natural numbers. The positive integers are also known as the natural numbers. And you can see this, of course, is a set. And a set is simply a collection of elements. They're not in any particular order. And I'm sure you've been exposed to sets before, but here it's important to note this is an infinite set. You can tell because of these 3 dots. This means that this pattern goes on forever, all the way up to positive infinity. So you can see 1, 2, 3, 4. These are the so-called natural numbers. Sometimes they're also known as the counting numbers. And you can see why, because these are the numbers that we use to count with. 1, 2, 3, 4. Obviously, when you count objects, you're using these numbers. Okay, so these are the natural numbers. Now, if you notice what's missing, there's no 0 in there, there's no negatives, and there's no fractional numbers. It's just the whole, sometimes they're called whole numbers or integers, and they're all positive. So these are the natural numbers. These would have been the first numbers developed by humanity, because in the early days, numbers were meant to be just useful. Like, in other words, I need to know how many chickens I have. Therefore, I count them, 1, 2, 3, 4, 5, that kind of thing. All the rest came later. As in fact, we're going to see a video later on in which we are introduced to a very brief history of math, which they discuss how this came about. Yes, they're sometimes called the counting numbers because they can be used, obviously, to count objects. This is where we first started out with the natural numbers. Now, here's something that you might have forgotten about. The natural numbers themselves can be decomposed into what are called factors. Let's take as an example 12. If I take 12, I want to know what natural numbers can I use whose product is equal to 12. And it turns out these are all of them. Okay, so clearly 1 times 12 equals 12, so does 2 times 6, and so does 3 times 4. So we say that 1, 2, 3, 4, 6, and 12 are the factors of 12. Another way to think about it is that each of these factors evenly divides 12. In other words, if I take 12 and divide by, let's say, 6, I'm going to get as an answer a natural number. Okay, so if any of these are divided into 12, the result will be a natural number with no remainder. Okay, so let's look at 24. Now, of course, it's the same thing. We're looking at the pairs of natural numbers whose product is equal to 24. And of course, you see there's more of them because 24 is a larger number. Okay. Now, it's not really that difficult to identify all these factors. It's more tedious than difficult, but we do have to be able to figure them out just by looking at the number itself. And, you can just go through the list and find the ones that work and don't work. Now, by the way, I want to point out that here, if you notice, I did not list 6 times 4 separately because it means the same thing as 4 times 6. Okay, we don't need it. All right. Now, divisible, yes. So just in the most general terms, the word divisible means here A and B are meant to be natural numbers. So we say that A is divisible by B if there is no remainder when A is divided by B. All right, so let's take an example. Let's say 24 over 8 is 3. So we say that 24 is divisible by 8. Sometimes you may have heard it written this way: 24 is evenly divisible by 8. And that just means that when we do the division, we get some kind of remainder, but there's no fractional. Oh, wait a minute. What did I do? Oh, right. Sorry, that's not the remainder. My fault. No, that's not right. Remainder means this. If I did 25 over 8, that would be 3 1/8. This would be the remainder. This is the quotient. This is the remainder. Okay, so this 3 would be the quotient. All right, now we're all set. So there's no remainder. There's just a quotient. Over here, there is a remainder. Therefore, 25 is not divisible by 8. Okay. All right, so we got that straight. And that's the reason why we're bringing this up now, of course, is because you can see that each number is divisible. Each integer is divisible by its own factors. Okay. So since 8 is a factor of 24, it must be the case that if I divide 24 by 8, I get 3. And it says here remainder of 0, but no remainder. It means the same thing as remainder of 0. Same thing with 6 and 24. If 6 is a factor of 24, it must be the case that 24 divided by 6 gives me a quotient, but no remainder. Now we're going to use this idea to define something that you're very familiar with. You haven't probably thought about this in a while. And what could that be? It's like an old friend coming to visit. It's prime numbers. That's right. When was the last time you thought about prime numbers? Well, it's probably been a long time. You don't even remember the last time you thought about prime numbers, do you? Well, but you know what they are when you see them, don't you? Okay. Intuitively, you know, for example, that 11 is prime, but 12 is not. Why? Well, here's why. A prime number is a number that has only two factors, 1 and itself. So there are no natural numbers that can evenly divide into 11, except for 11 itself and the 1, of course. Okay, so 12 is different. I can take 12 and divide by 6 and get 2, no remainder. So that means 12 can't be prime. All right, or else we can just remind ourselves that 12 has factors of 1, 2, 3, 4, 6, and 12. And because it has more than these two, it has all the rest of these, therefore it must not be prime. Whereas 11 has factors only of 1 and 11. That's it. And that's why it's prime. 7, of course, is another classic example. The only whole numbers or natural numbers that evenly divide into 7 are 1 and 7. Oh, it's been a while, hasn't it? Yes. So why don't we make up a short list of the prime numbers, the first few prime numbers, just to remind ourselves how that works. Now, before we do that, though, I do want to mention, here's a very strange result, though. Yeah, 12 is not prime because it has factors other than 1 and 12. This might surprise you, but it turns out that 1 is not considered to be a prime number. It's not because there's only one factor. A prime number has to have 2 factors. They have to be unique, I should say. 1 and itself. But here, the only factor of 1 is 1. So therefore, 1 only has 1 factor. So it is not prime. It's kind of bizarre, but it's not. So we have to keep that in the back of our minds as we do the following sections. 1 is not formally defined as a prime number. So, but that's the only exception. The rest of them make perfect sense. For example, here's the next, or the first 10. So you see, what do they all have in common? There's no natural number other than that number and 1 that can evenly divide into that number. And you can go on and on and on and on. Now, prime numbers are surprisingly difficult to calculate. You'd think that computers could do this very easily, but apparently it's a much bigger challenge than you might think. Now, here's an example right off the bat. Already, I can think of a good way to show you how this is used in practice. You all have probably used Amazon.com. I don't even need to do a poll. If I do a poll right now and say, have you ever used Amazon? I'm going to expect 100% say yes. Now, here's the big question. How do you get your information to them? You type it in there and you put in your credit card number, and zoom, your order goes to Amazon and the package arrives at your house in a day or two. Here's the question. What's there to stop crooks from reading your number on the internet? Your credit card number. In other words, you type in that number and somehow it gets to Amazon safely without crooks being able to read it. How is this happening? Well, what's happening is that the data entered into Amazon's website, and all of them are called encrypted. Now, that means that they are converted into a special code that only Amazon knows, so that if somebody did somehow managed to read that information, it wouldn't make any sense to them. It's a code that only Amazon knows. And so the key here is that this is actually a very major area of law enforcement. And the FBI has people who just do this kind of stuff all day long. And so the key to all of this, and the reason why I'm bringing it up, is because the techniques used to create these codes are usually based on prime numbers. Yes, they're heavily used in the creation of these special codes. Now, I know about this because I know somebody who actually is a specialist in this area. And when he tells me about it, I can understand about 2% of what he's telling me. But I do know that that a lot of this work is based on prime numbers. So there you go. Already, there's an application that you may have encountered in your daily life. You ordered stuff from Amazon, and without knowing it, your credit card number was turned into a code, and to keep it safe, and most likely that code was based on prime numbers. Now, when that code gets to Amazon, then they reinterpret it and convert it back to your actual credit card number so that they can actually, take the money. Interesting. There's a lot of and that just scratches the surface as far as applications of prime numbers. They're very mysterious objects. Mathematicians have been fascinated about them for centuries. In fact, Maybe if I'm lucky, I'll be able to find a video about prime numbers. And if I do, I'll show it to you, let's say on Thursday. But in the meantime, you're probably wondering then, if a number is not prime, what should we call it? Well, there's a name for it, of course. And it's not, non-prime. There's an actual formal name for numbers that are not prime. All right, hold on a second. I'm cleaning up these notes as we speak. Here we go. It's called a composite number. Okay. In other words, any natural number which is not prime is said to be composite, which guarantees that it has at least three factors: one, itself, and at least one other number. So here, for example, 22 is considered to be composite because, yes, it has 1 and 22 as its factors, but it also has 2 and 11. So it's clearly not prime. In fact, it is said to be composite. So all the natural numbers are either prime or composite. That's all we have to choose from. Okay. All right. So all the natural numbers are either one or the other. Now we're going to use this information to do something very, very interesting. You'll see as we go along. Eventually, we're going to catch up with a concept that you've seen before, but not maybe for a while. It turns out that the factors of any natural numbers can be written in more than one way. But all the natural numbers can be written as a unique set of prime numbers, okay, and which we will call prime factors. All right, so let's see how this works. Now it sounds very, very high-powered, very impressive, and all. The fundamental theorem of arithmetic. You can rest assured the proof is very complicated, but it gives us a very useful tool, which we'll see in a few minutes, how handy it can be to be able to take all these natural numbers and write them not just as a set of factors, but of prime factors. All right, now, for example, here's the 12. Now, we know that 12 has many different factors, including, let's say, 2 and 6 and 3 and 4. How would we rewrite this as a series of prime numbers? Good question. Well, let's start with 2 and 6. The 6 itself is 2 times 3. So 12 equals 2 times 6. And in turn, 6 equals 2 times 3. So it stands to reason that 12 could be written as 2 times 2 times 3. And these are all prime numbers. So we would say that 2 times 2 times 3 is the prime factorization of 12. Now, what if I had chosen to do this? I choose 4 and 3, but I recognize that 4 equals 2 times 2. That tells me that 12 can be written as, oh, it's the same. Look at that. So it turns out that each natural number has exactly one way, one prime factorization, and that's it. It doesn't matter how you calculate it. You're always going to wind up with the same result. Okay, now, there it is. Okay, so we've already covered this. Now, I'm going to show you an alternative way of getting to this result, which I think you'll find to be a little bit easier to follow. I'm going to create a diagram. Let's start with the 12. All right, we start at the top. We're going to create what's called a binary tree. And the key here is this prefix bi is used in English to represent 2. Okay, by 2. Now, what I'm going to do is draw 2 branches that represent the factors of 12, 2, let's say, and 6. And now 2 is prime, so I'm not going to go any further along this branch, but 6 is not prime, so I'm going to break that down into 2 times 3. And these are both prime numbers, so I can stop what I'm doing. And what I'm going to notice is that these are all prime factors of 12. So I can say that 12 equals 2 times 2 times 3. I think you'll agree that that's a pretty straightforward way of finding the prime factors of any natural number. Now, I'll also show you the other one. Suppose I'd started out with 3 times 4. We have already seen that it gives us the same result, but let's try it again with this little diagram. Okay. Let me draw it on the next slide. This time I'll start with 12 is 3 times 4. This is a prime number, so I stop here, and now this is 2 times 2. Now you'll notice the order doesn't really matter. This can be written as 2 times 2 times 3. It is the same thing as what we had before. So these trees will make it, I think, a lot easier for you to find all the prime factors that you need for any natural number. Now, of course, if you have a prime number, this isn't going to get you anywhere. This only works with the composite numbers. The prime numbers, it's understood that we don't have any other factors besides 1 and the number itself. But for these cases, we do. Now, what are we going to use these for? Well, there's a couple of, at least one interesting application. So again, I'm going to show you a concept that you've probably seen before, and it's probably been a while, and that would be greatest common factors, also sometimes known as greatest common denominators. Oh, does that ring a bell? Of course it does. It rings a lot of bells. You're like, oh my God, I remember this. It wasn't that long ago, was it? What exactly is a greatest common factor? Okay, starting with 2 numbers like, let's say, 18 and 24, we're going to find the largest natural number that evenly divides both 18 and 24. Okay, so let's do it. Now, it turns out that you can just sit there and look at them and hope that you can find what you're looking for. You could write out a list. Like, for example, 18, let me write 24 next to it. So we don't need the 1 and the 18. So here we have 2 and 12, and 3 and 8, and 4 and 6. If you look at the list, you'll see that the largest factor that they have in common is the 6. And that's fine as far as it goes, but there's a quicker and easier way of doing this, which involves the prime factors. Let's find out what it is. What we're going to do instead is use our trees. Let's start with 18. 2 times 9. We can stop here because this is a prime. Yeah, here we go. And over here, let's do 24. We can stop here because this is prime. The 6 is not prime, so we'll keep going. And oh, here we go. So for 18, the factorization is 2 times 2 times 3. For 24, it's 2 times 2 times 2 times 3. Now, what we're going to do is look for the factors, the prime factors that they have in common. Well, they both have a pair of 2's, and they both have a 3. And let's see. Oh, yeah, that's right. No, I wrote it. Oh, I'm sorry. I wrote it wrong. No wonder. I was going to say something's not right here. I copied it wrong. Okay. 2 times 3 times 3. That's my fault. All right, let's do that again. This is 2 times 3 times 3. This is 2, 2, 2, 3. What do they have in common? They have a 2 and they have a 3. So that means the greatest common factor is 2 times 3, which is 6. All right, so I mean, of course, there's more than one way of doing anything in math. So for finding greatest common factors, this is a fairly straightforward approach where, again, you're just taking each of the two numbers, you break it down to the prime factorization, and you look at what prime factors they have in common. And the product of those common factors is what you're looking for. In this case, 6. All right. Well, that was pretty interesting. Now, you probably needed to do this on the SAT that you took to get into college. And on the math section, you probably were asked to do at least one greatest common factor. Oh, if only you'd known about this technique at the time. But that's all right. Those days are over. No more SATs for you. All right, now. How about, oh, and by the way, you can check this out too. If you take the 6 and divide it into both of your numbers, you'll see that you're getting no remainders. All right, now, here's the challenge for the day. Now that you know how this works, I hope you will have paper in front of you. What I'd like you to do, without my showing you the answer, is do the same thing for 72 and 180. So in other words, you create the tree for both of them and identify the common factors. All right, are you up for this challenge? Yes, I know that it's a cold, miserable Monday morning, but yes, you are. In fact, you're kind of psyched. You're pumped up to do this and show me what you can do. So, all right, I'll give you a couple of minutes and then you let me know what you came up with. I don't have any prizes to give out to whoever comes up with it first, but you'll have the pride of knowing that you understand what we're doing. Oh, we have an answer. Let's see what we got. Oh my God, you guys are fast. It is 36. Yes, it is. Wow, I'm impressed. First day back and you're already on the ball. No, it is 36. So let's see why. There's a discussion here with the actual factors, but I'm going to show you the graphs because I think you'll like that better. Oh no, sorry about that. But all right, thumbs. Oh, I didn't know you could have a thumbs up in this thing. Okay. All right, let me show you how that works with the graphs. All right, here we go. So let's go back here. $72 and $180. Okay, now of course the pattern that you use to go through the tree is not really important. As long as you find all the factors. I usually start with the smallest numbers that I can find. Okay, so you've got 2 times 2 times 2 times 3 times 3 over here. Over here you've got 2 and 90, 2 and 45, 5 and 9, 3 and 3. Okay, so 180 equals 2 times 2 times 3 times 3 times 5. And so what do they have in common? They both have 2 2s and 2 3s. So the greatest common factor is 2 times 2 times 3 times 3, which is 36. And so again, if you divide 36 into 72, you'll get a 2 with no remainder. And if you divide it into 180, you'll get a 5 with no remainder. So that means you must have done it correctly. But the key to the whole thing is this little chart or graph. And again, when you're done, you have your prime factorization. And whatever they have in common is what you use for your greatest common factor. That to me is the quickest way of doing this. All right. Now, it turns out you can actually do this for more than 2 numbers at a time. All right. So I'll tell you what, this time, I don't want to rush anyone. Let's try it with these 3 numbers, and then I'll wait till everybody's done before I announce the answer. How about that? Okay. So we're going to do all 3 of these. And of course, it just means create 3 trees and look at what they have in common. All right. So I'll give you a couple of minutes and then we'll figure out what happened. Okay. Everyone's done? Oh, okay. Well, we'll wait another minute or so. There's no rush. Like I said, I mean, it's the first day. All right. All right. So anyone think they know what it is? It is indeed 24. Very good. Oh my God, what a class. I can see there's going to be a lot of A's in this class. All right, let me show you the diagrams. Let's see, what do we have here? 24. I'm not sure if I can fit them all in one slide, but let's give it a shot. 24 can be broken down into 2, 12, 2, 6, 2, 3. Okay, 72, we've already seen this one. All right, I'll do 120 on the next page. Okay, so they're all done. So 24 is 2 times 2 times 2 times 3, 72, 2, 2, 2, 3, 3. And then finally 120 is 2, 2, 2, 3, 5. So yeah, they all seem to have in common 3 2s and a 3. So the greatest common factor between all three of them is 2 times 2 times 2 times 3, which is 24. So 24 is the greatest common factor of itself. Okay, which is true. I mean, with the other two as well. Okay, great. Well, that was pretty nice. So, all right, I'll tell you what. Now, I did mention that I do have a video about the history of math that I think you should see today. Good, 24, beautiful. Now, in the past when I've done this, I'm showing these videos, and this is all being recorded. And then what happened was YouTube, one day, completely out of nowhere, YouTube said, "Hey, you're not supposed to be recording those videos that other people made." So when this is going on, I'm going to have to pause the recording. I hope this works. This pause share button seems to be the way to go. If somehow we get disconnected or something, we'll try to figure out how to get back in. But I think this is all that I have to do. Now, the only drawback to this is that whoever is watching this later on is not going to see the video again. But the lists of videos are on Moodle anyway, so it shouldn't be a problem. Let me go find that. I made a separate category for video. So if you click this on, it should literally take you right to the YouTube video. So what I would like you to do while we're pausing is I'm going to have you watch this video on your own computer. The sound was always a problem anyways, and we ended up having to do it that way in the past. But what I'm also going to be doing is pausing the recording so it will not appear in the video. Just because you never know, it could cause problems, and we don't want that. So why don't we all do this? Go to the Moodle right now and click on this link to the history of math. Before we get too far ahead, I want you to see this because it's a very interesting video and covers some of the topics we'll be looking at. And so it's probably no more than 5 or 6 minutes long anyway. So why don't we all grab that video, and then I'm going to pause the sharing right now. There it goes. So that means, can you all still see me, or is it just the recording that stopped? Oh, all right. I can't tell, but all right, let's watch this thing.
Yeah, we can still see you.
Oh, okay, good. All right. So I'm going to turn it on here so I know how long it lasts. And so that's good because I've never done this before. Good. All right. So we'll all watch it at the same time. And when we're done, we'll get back together and then we'll talk about how cool it was. And we'll carry on from there. Okay. All right. Let's do this. For solutions to basic problems. Mm. Yes, I agree. I guess I can undo it right here. There we go. Yes, no, that's why I picked it for this class because I thought it was a very good background. You can see how numbers evolved over the many, many centuries. In fact, they mentioned early on the Babylonians created their numbering system. He said the fourth millennium BC. That's going back a ways. And you can see that even in ancient times, people were trading with each other, and they had to have some system for keeping track of who owed what to who, and or how many products you had, or how much you were bringing to market. So they had to think about these things a very long time ago. And of course, the evolution of the math accelerated very quickly in recent years. But you know, a lot of what the numbers that we use, a lot of the ideas have been around for thousands and thousands of years. It's very surprising and very interesting too. So, like for example, the idea that zero, as we'll see, we're going to see another video about zero very soon. It wasn't really commonly used until quite relatively recently. Nobody would have thought that zero was needed. I mean, what does it represent? It represents nothing. And I don't, they didn't mention it, but the idea of negative numbers would have come along even later than that. So yeah, the history of math is actually quite interesting. All right, anyway, so what I wanted to do is just quickly show you one more concept, which is something that you probably remember as well. Around the same time you were introduced to the concept of greatest common factor, you would probably have been introduced to this notion of the least common multiple. Yes, remember that? The least common multiple. What is that all about? Well, first of all, what is a multiple? A multiple, it means you take a number like, let's say 18, and you multiply it by all the natural numbers. So each of these is a multiple of 18. 18 itself, 36, 54, 72, and it goes on and on and on. These are all considered to be multiples of 18. They're simply, in each case, you take one of the natural numbers and you multiply it by the 18 to come up with all these multiples. Now, if you needed to know for whatever reason what the smallest multiple two numbers have in common is, this is actually a pretty straightforward technique. There might be more sophisticated ways of doing this, but usually, oh, and here's 24. Your best bet is typically to simply write them out until you find the smallest one that they have in common. Like in this case, for example, if you wanted to find the least common multiple of 18 and 24, I've literally just written a list of both of them. And then you can see by looking at the two lists that, where are we? We're looking for, here it is. The smallest one they have in common is 72. And so therefore, the least common multiple is 72. Now, it is possible. I know one of the classes one year, somebody was showing me a technique that they'd been taught for doing this, but it seemed to me that it was more complicated than this. So I think we'll stick with this approach. Now, your challenge is to find the least common multiple for 72 and 180. And remember, the multiples are simply all of the, in order to get multiples, you multiply that number by natural numbers, and then you can stop basically when you find the one you're looking for. All right, so let me give you a couple of minutes and let's see what you can do. Okay, good. Let's see if everybody else is ready. All right. We're good. All right. All right. Let's check it out. So I've made a short list here of the first 5 for 72, and then the same thing for 180. And then I've written them from left to right, so it's easier to see. And if you look across, you'll see that, what do they have in common? Ah, here we go. 360. And it's just that simple. The only tricky part is knowing when to stop multiplying. Like, how far out do I go? Well, you just have to, it's basically trial and error, but it's not that difficult. I think you'll find that this is a little bit more simple than what we were doing with the greatest common factor. But still, as long as the numbers are not too enormous, you can do this pretty straight, in a very straightforward way. All right, well, you know what? I just realized we just finished chapter 5A. Oh my God. Well, that was a lot for the first day. Now, you know, the cameras are kind of optional. I mean, it would be kind of nice if I could see what you look like, but I don't want to insist on it either. I know some teachers do that. They make sure everybody has their camera on, mainly because they want to make sure that you're paying attention. Well, I assume that that's the case. If you want your picture showing, that's fine with me, but I will never insist on it. Okay. So, it's completely up to you if you want to have your picture. I would love to see what you look like. I mean, I have a picture on the roster, but it's not the same. You know how it is. You know how badly school IDs often turn out. I'm sure you've seen yours, and it's maybe not the best picture you've ever seen of yourself. In fact, it might be the worst, but yeah, it's completely up to you. All right. So now, God, what time is it? I have to keep track. You know, when the semester starts rolling along, I've got the timing in the back of my mind just right. Right now, we've been off for several weeks, and so I have to consult my clock here. It's almost 10 o'clock, and it's the first day. So I think, why don't we stop right here with the understanding that you will go to Moodle, and here it is. Download 5B and just start looking at it so you can see where we're going on Thursday. And I do actually have at least a few more very cool videos that we will be able to look at on Thursday as well. And one of them involves the surprisingly interesting history of zero. Okay, you might not think that zero would have an exciting history, but it does. So that's one of the many things we'll be looking at. In the meantime, you can download these slides and hang on to them. You should probably flip through them and remind yourself what we were doing. And again, don't forget that not just yet, it takes a while for the video to be processed, but sometime today, this video will be in my YouTube account and you can go watch it anytime you want to. So anyway, all right, I guess that will be it for today. And I guess I'll just see you all on Thursday. All right, unless there's any last minute questions. All right, great. All right, well, congratulations. You made it through your first class of the semester. All right.
Thank you very much. Take care.
Right. You're welcome. See you Thursday.
Thank you. See you
Okay.
Thursday.
All right, see you Thursday. Bye.
Thank you.
Bye.